Hello, wishing everyone a good day. Have a nice day. So, I'll be teaching you how to solve problems on regenerative Rankine cycle today. Okay, so first thing, let us take a look at the question or the problems. Okay, so now a single heater regenerative cycle. The steam enters the turbine at 30 bar and 400 degrees C, and the exhaust pressure is 0.1 bar. So 30 bar would be the boiler pressure, and 0.1 bar would be the condenser pressure. The feed water heater is a direct contact type, which operates at a pressure of 5 bar. So at this pressure, steam is being extracted from the turbine as well, which is directed to the open feed water heater later. Now find the efficiency and the steam rate of the cycle. Pump work may be neglected. Okay, so this will be the schematic diagram which shows you the boiler. Okay, so the steam that is coming out from the boiler is at a pressure of 30 bar and 400 degrees C. So based on this, we know that at state point 1, the steam actually is superheated. So it goes into the turbine. Supposedly, it should be going through an isentropic expansion, but somewhere in between, at a certain pressure, a certain amount of steam, hot steam, is extracted from the turbine with a mass of m kg. So it will goes into the open feed water heater where it mixes with the saturated liquid that leaves the condenser. Okay, so then you have full isentropic expansion after that from 2 to 3, where state point 3 is actually the exit of the turbine, and it goes into the condenser where it undergoes a constant pressure cooling process. Then it goes into the feed pump where saturated liquid is being pumped into the open feed water heater. Then in the open feed water heater, the saturated liquid just now will be mixing with the blade steam that has been extracted from the turbine at pressure 5 bar. Then it goes into the next pump where it is being pumped into the boiler, which increase the pressure, the pump supposedly to be increasing the pressure and temperature of the boiler. So now the next would be the TS diagram. So from the TS diagram, you can see there should be 3 pressure lines. One is based on the boiler pressure 30 bar. Then the middle one, which is the 5 bar, this one is the pressure at which steam is being extracted from the turbine as blade steam. Then the lowest pressure is 0.1 bar. Then when you look at state point 1 to 2 and then from 2 to 3, can see full expansion in the turbine where it undergoes in an isentropic process where S1 equals to S2 and it should be equals to S3 as well. So initially, okay, the amount of steam, we assume that is 1 kg. Then at state point 2, the amount of steam extracted will be m kg. So the remainder will be 1 minus m kg, which goes into the condenser. Then after that, okay, it goes into the open feed water heater where it mixes, okay, with the saturated liquid mixed with the blade steam earlier in the open feed water heater. So this is the table that I've prepared with pressure, saturation, temperature, and enthalpies and also entropies of saturated liquid, dry saturated vapor. So with a pressure of 0.1 bar, 5 bar, and 30 bar. Now all these data are extracted from the property tables. So from here, you can see this is the TS and this would be the HS diagram. Okay, so from the HS diagram, you can also see that there are three pressure line, constant pressure line, that is 30, 5, and 0.1 bar. And here it shows you the isentropic process from 1 to 2, and then from 2 to 3. So these are the data which has been extracted from the property table as well, based on pressure 30 bar and 400 degrees C, where the condition of the steam is superheated. Okay, so because when we take a look or when we compare the pressure 30 bar from the normal condition and the superheated, you can see that the temperature here is 400 degrees C, whereas the saturation temperature is only 233.8. The given temperature is 400, which is greater than the saturation temperature. So that is why we can justify that the steam is superheated. And from that, what we need is usually the enthalpy and as well as the entropy for state point 1. So state point 1, we can say that the steam is actually superheated. Okay, so at 30 bar and 400 degrees C. So you got your H1, that is 3230.9 from the table. And then the entropy of 6.921, also from the table. Then once we have found the enthalpy and the entropy for state point 1, we can proceed with state point 2. But bear in mind that S1 is equals to S2. Okay, remember S1 is equals to S2 because it's an isentropic process. So for state point 2, the steam is again superheated, but the pressure now is 5 bar with the entropy of S2, which is equals to S1 of 6.921. Okay, why we say S1 is S2? Because it is an isentropic process, means constant entropy. So from the table that I have given you here, okay, for the superheated section, there is no entropy in as shown in the table. So what we can do is now we take a look at the table, a clearer look at the table. What is given is only 6.822 and 7.060. So where the 6.921 lies in between these two entropy. So if let's say for example we want to find the enthalpy at 6.921 kilojoules per kg of entropy, what we have to do is interpolation. So by interpolation, so I have written it down in a proper table like this, where you have your 5 bar, okay, and then at temperature 151.8 you have enthalpy 2749. At temperature 200 you have 2857. So and at the same pressure, entropy which is at this temperature is 6.822 and at this temperature is 7.060. So what we have is the entropy of S2, which is equals to S1 6.921. So with these three values and with these two enthalpy, by interpolation, we will be able to find out this H2 here. So from here, I will show you what I have done for the interpolation. Okay, so basically what we need is H2. So from here, we will be able to find out H2 is 2794.1 kilojoules per kg. These are the interpolation, okay, for these data here to find the enthalpy of H2. Then we move to state point 3. As from the diagram, you can see that state point 3 is actually lying inside the saturation dome. So we can say that state point 3 is in the wet stage. That means the wet condition. That means the mixture of liquid and vapor. And we usually call it as wet steam or wet vapor, which is at this pressure here. That is 0.1 bar, and with the entropy of 6.921, which is equals to S2 and as well as the S1. So since we know that 0.3 is a wet vapor, so what we can do is we can find out the dryness fraction by applying this formula here. Okay, so once when we have found this dryness fraction, we can actually find the enthalpy later on. So from this, we got that the dryness fraction or the quality of steam is 0.836, which is still considered as low quality. So dryness fraction of 0.836. So let us substitute the x into this to find out the enthalpy at state point 3. So this is your HF and this would be your HFG. So you got H3 of 2191.7 kilojoules per kg. That is for state point 3. Okay, so now then after that we move to state point 4 and as well as state point 6. Now we will not be looking at state point 5 and state point 7, that is here and here, since we neglect feed pump. So if let's say we neglect the feed pump here, let us just cover off this part. So the enthalpy that involved is only the H4 and the H6. If we cover off this part here, neglecting the pump, so we will consider H6 and H4. So the next we have to find H4 and H6. So when we look into the TS diagram, we got to know that 0.4 is sitting, 0.4 and 0.6 is sitting on the saturated liquid line. So therefore, H4 and H6 should be the enthalpy of the saturated liquid. So H4 you refers to 0.1 bar, H6 you refers to 5 bar, which I have given here. That is 640 and 192. So state point 4, which is this saturated liquid condition at 0.1 bar. So we got to know that at this point, H4 will be the HF at the pressure of 0.1 bar. So that is the value that we should consider. So then the next thing is we move to state point 6. Remember, we don't have to find the state point 5 enthalpy and the enthalpy of state point 7 as well, because we neglect the feed pump work. So state point 6 is also sitting on the saturated liquid line. So therefore, we take H6 is actually at pressure 5 bar and is equals to the HF. So the value is 640. So you have H6 is 640 kilojoules per kg. Then after that, the next thing we have to find is the amount of blade steam. Okay, blade steam. So which is the amount of steam which we extract, which is being extracted from the turbine for the purpose of heating here. That is mixing with the saturated liquid that goes or which enters the open feed water heater from the condenser. So from the open feed water heater, okay, so there are 1 line, 2 line, and 3. So both of this line here is actually the one that is going into the open feed water heater, and this line here, line 6, is actually leaving the open feed water heater. So what we can do is we apply energy balance for this. So we have, okay, the mass kg with H2 plus the quantity here 1 minus m with the enthalpy of H4. Please don't forget we have neglected the pump, so that means 0.5 doesn't exist. Okay, so we have this. So and then we have the mass on one side and the one that is without the m on the other side. So from here we will be able to find out the mass of the blade steam, okay, or the steam which is extracted from the turbine. So you have the enthalpy H6, H4 and H2. So just substitute and you get the mass of blade steam is in kg per kg of steam supplied to the turbine per kg. Okay, so we got the M. Then we move on with the work output, heat supply and heat rejected. So work input is being neglected. Remember, we neglect the feed pump work. So these are the enthalpies we have got from H1 to H6 without H5 and H7. So I have listed down in the table. So turbine work output basically is this portion here, this section here from 1 to 2 and from 2 to 3. And don't forget from section 2 to 3, since an amount of steam has been extracted in some way in between within the turbine, so therefore the amount of steam we consider here would be 1 minus m. So work done from 1 to 2 can simply say it is H1 minus H2, but we multiply by 1 kg. Okay, you can multiply by the 1 or you don't have to. Okay, 1 minus m, that is the amount of steam in kg for this section here, 2 to 3. So for the work done from 2 to 3, therefore we have to multiply by this mass here. So what we have is H1 minus H2 plus this, and then H2 minus H3 for the work output or the turbine work. So we got a work output of 912.7 or the turbine work as 912.7. So since net work out is equals to work out minus work in or heat supply minus heat rejected, and since we have neglected the work in, so we can say that net work out is actually equals to the work out itself. That means the turbine work, the total turbine work. Okay, so I have put an explanation here. So the net work out, which is also the turbine work, so is equals to 912.7. So the next thing we need to find would be the heat supply that is based on the boiler at constant pressure. So heat supply would be equals to the heat from 6 to 1. Remember, we have neglected the feed pump work, so we don't consider H7. So therefore, heat supply would be equals to H1 minus H6. So that would be the heat supply. So from there, we can find out the cycle efficiency, which is net work over heat supply. So we got 35.2%. Then if we want to find the specific steam consumption, then we just simply take 3,600 divided by the net work, which is 912.7. So we got 3.94 kilograms per kilowatt hour for the specific steam consumption. That's all for this problem. So we will proceed with the rest of the problems later on. So thank you very much and stay safe. Hello everyone, welcome to my class again. So we'll be doing or solving some problems today on regenerative Rankine cycle. So first take a look at the questions. So a steam turbine fed with steam having an enthalpy of 3100 kilojoules per kg. So this is the enthalpy of the steam at the inlet of the turbine. Then it moves out of the turbine with an enthalpy of 2100 kilojoules per kg. So that refers to the turbine exit because it moves out. Then feed heating process is done at a pressure of 3.2 bar. So this is the pressure at which steam is extracted from the turbine for the process of mixing. So, and we call it as the blade steam. So the enthalpy of that is 2500 kilojoules per kg. Then the condensate from the condenser, that means the exit from the exit of the condenser, the enthalpy is 125 kilojoules per kg, which would be the enthalpy of the saturated liquid leaving the condenser. Now the quantity of blade steam is 11,200 kilograms per hour. Now then, the question asks us to find the power developed by the turbine and also assume that the water leaving the feed heater is saturated liquid at 3.2 bar. Okay, so which would be the condition of the saturated liquid before entering the boiler again. Now, and the heater is direct mixing type, and then we have to neglect pump work. So this would be the schematic diagram showing you the boiler, turbine, open feed water heater, pumps, we have two pumps, and the condenser. And then we have amount of mkg of steam extracted from the turbine at a pressure of 3.2 bar. That is given in the question. Then here would be the exit of the turbine, exit from the turbine with a mass of 1 minus mkg. Okay, and then this would be the condenser. This would be the saturated liquid with the mass of 1 minus mkg. So what I have done is I have listed down all the enthalpies for each of these state points from 1, 2, 3, 4, and 6, which I have neglected the pump here and the pump here. So we will be looking at state point 4 and state point 6 only without the feed pump. So for the adiabatic mixing process based on the open feed water heater, we have two inlets and one outlet. The inlets are from first stream 2, and then the second one is from the fourth state point. So from state point 2, where certain amount of steam being extracted from the turbine, you have mass mkg and enthalpy which is at 5 bar H2. So H2 would be equals to 2500 kilojoules per kg, and then the second inlet would be at 0.1 bar with enthalpy H4 with a mass of 1 minus m. And then the outlet, before it reaches the boiler, you have pressure 5 bar with the enthalpy of H6. So during this mixing process, what we have to do is we have to consider the energy balance and the mass balance. So based on the diagram here, we have 2 inlets and 1 outlet. So what we can do is we take the inlet plus the next inlet. That means we add up both the inlets and equate it with the outlets. Okay, so for energy balance, we have the inlet MH2 and also 1 minus MH4. The outlet that we have would be this, which is H6 and is 1 kg. Based on the initial, okay, steam of 1 kg. So by manipulating this equation here, what we can do is the terms or the enthalpy with the M, we will put it onto the left hand side, and then those without, we will put it onto the right hand side. So the equations will look something like that. Okay, so from this we have mass is equals to H6 minus H4 divided by H2 minus H4. So what we can do is we substitute the H6, which we have found from the HF at 3.2 bar. The pressure here will be 3.2 bar and the enthalpy here is HF, saturated liquid. And we have 570.9 for H6. Okay, and then H4 we have 125, and then H2 we have 2500. So substitute everything, we will be able to find out the mass of blade steam per kg of steam that is applied to the turbine. So the M is 0.188. Please take note of this. This is kg of blade steam per kg of steam supplied to the turbine. So based on this, how much we have extracted, which is 0.188. So for turbine work, we know that, okay, we have to take H1 minus H2 for the initial stage, and then H2 minus H3 when the amount of a certain amount of mass or blade steam has been extracted from the turbine. So the remainder of the expansion work we take is H2 minus H3. Okay, so we have the work, the turbine work, or the work output as work from 1 to 2, which you multiply by 1 kg, and then 1 minus M, that is the mass, then multiply by the work from 2 to 3. So the amount of turbine work, we have the enthalpy of H1 minus H2, then the H2 minus H3. So what we need to do is just substitute all the enthalpies here and the mass of blade steam here. So we will be able to find the turbine work as 924.8 kilojoules per kg of steam that is applied to the turbine. So the next is when we look at the steam supplied to the turbine per hour. So that is given in the question, 11,200 kilogram of blade steam per hour. So since we have kilogram of blade steam per kilogram of steam supplied to the turbine earlier, so if let's say for example we want to find 1 kg of steam supplied to turbine in 1 hour, then we have to take this divided by 0.188. This is mathematically, okay? So you got 59574.5 kilograms per hour steam is supplied to the turbine. Okay, so steam supplied to the turbine per second. So what you need to do is divide it by dividing it by 3600. Okay, so you have 16.55 kilograms per second. Then the power developed by the turbine, usually we take the mass flow multiplied by the work out. So power developed would be therefore 924.8 kilojoules per kg multiplied by this 16.55 kg per second. So you will have kilojoules per second, which is kilowatts. So this would be our answer. That would be the power developed by the turbine. So that is 15,305 kilowatts. Thank you. That is the end of this session or this problem here. Okay, I will see you in the next problem. Thank you. Bye. Today we will be doing or solving problems on regenerative Rankine cycle. So first thing, let us take a look at the question. Now, a steam turbine is to operate on a simple regenerative Rankine cycle. Now, steam is supplied dry saturated at 40 bar. So this will be the boiler pressure and is exhausted to a condenser at 0.07 bar. So this pressure would be the condenser pressure. So the condensate is pumped to a pressure of 3.5 bar, which is the pressure at which the steam is extracted from the turbine, okay, for regeneration purposes, okay, at which it is mixed with blade steam from the turbine at 3.5 bar. Now the resulting water, which is at saturation temperature, is then pumped to the boiler to complete the cycle. Okay, so for the ideal cycle, calculate and neglecting feed pump work. First, the amount of blade steam required per kilogram of supply steam. Part 2, the cycle efficiency of the plant. And then part 3, the specific steam consumption. So now the table here is showing, okay, the data at various pressure, which is the condenser pressure, and this is the intermediate pressure or the pressure at which the steam is extracted from the turbine for mixing purposes. And then you have the boiler pressure of 40 bar. So we have the enthalpy of saturated liquid, the enthalpy of dry saturated vapor, the entropy of saturated liquid, and the entropy of the dry saturated vapor, all listed and extracted from the property tables. So this will be the schematic diagram for the regenerative Rankine cycle. So you have devices like boiler, which operate at constant pressure, and then you have turbine, which you have isentropic expansion. Then you have the condenser, which you have constant pressure cooling. Pump 1 and pump 2 that serve as the purpose of compressing or bringing up the pressure and temperature, 1 to the open feed water heater, 2 to the boiler pressure. And then this would be the TS diagram. So when it refers to point 1 and the schematic diagram point 1, so that would be the inlet to the turbine. So it will undergo an isentropic expansion from state point 1 to 2. And at the state point 2 here, the amount of X kg of steam is being extracted, okay, for mixing purposes. That would be here in the schematic diagram. Then it undergoes full expansion from state point 2 to state point 3, where it is going to go into the condenser. So in the condenser, it will undergoes constant pressure cooling to point 4, where it reaches its saturated liquid condition. And then it goes into the first pump, where it undergoes isentropic compression to state point 5 here and 5 here. Okay, then it mixes with the blade steam just now, which is from state point 2. Then it reaches a stage of state point 6. And then it goes into the second pump, where it undergoes isentropic compression to bring up the pressure and temperature of the working substance to the boiler pressure, which is 40 bar. And then the cycle repeats thereafter. So these are the data we have, and the schematic diagram and the TS diagram. So it's basically for online purposes. So all these, in each slide, I have to show the table, the schematic diagram and the TS diagram, so it is easier for me to explain what happens at each state point. So first we start with state point 1, which is dry saturated and at the pressure of 40 bar, which is the boiler pressure. So from the boiler pressure in the table, so you search 40 bar here and you look for Hg, that is the enthalpy of the dry saturated vapor. So you have 2801. So H1 actually would be equals to the Hg at 40 bar. And then S1 will be equals to Sg at 40 bar. So you have 6.070. So remember, state point 1 to 2 and from 2 to 3, they undergoes isentropic expansion. So therefore, when you look at the diagram, the TS diagram here, the entropy are constant. So we can make use of the entropy of state point 1 actually to find out the dryness fraction at point 2 and the dryness fraction at point 3 later on. So at state point 2, we know that at the beginning, okay, it is an isentropic, so the entropy is constant. So S2 will be equals to 6.070 as well. So by looking at or by applying this formula here, we will be able to find out the dryness fraction that is at state point 2, which is 0.83. So apply this into the enthalpy formula for the mixture. So you have HF and X HFG. And please bear in mind that at state point 2 here, the pressure is 3.5 bar. The entropy also, you have to refer to the pressure of 3.5 bar here. So for the enthalpy HF, that is the saturated liquid enthalpy 584, and then the HFG, that is 2148. So to obtain HFG in case, you have to take Hg minus HF. So you have 2148. So you will be able to get the enthalpy H2 or at state point 2, 2373.176 kilojoules per kg. Then after that, we can move forward to state point 3. So at state point 3, the same thing, because we know that this vertical line here indicates constant entropy. So the entropy are constants. So we can take S3 to be equals to 6.070 kilojoules per kg Kelvin as well. So from that, again, we find the dryness fraction, but this time is for the point 3. So state point 3 dryness fraction would be 0.714. Bear in mind that state point 3 is sitting on the condenser pressure. So you have to refer to pressure 0.07 bar for SF, 0.559, and for the SFG, okay, 7.715 here. Okay, 7.715, sorry for that. Okay, so you will be getting a dryness fraction of 0.714. Then after that, you have H3. Apply the dryness fraction in order to find H3. Remember HF3 and HFG3, we will have to refer to the condenser pressure, that is 0.07. So our HF3 is 163, HFG is 2409 with a dryness fraction of 0.714. So you will have H3 of 1883.8. Then we move forward to state point 4, which is a bit easier. So if we want to find H4, and we know that state point 4 is actually sitting on the saturated liquid line, and state point 4 is at a condenser pressure of 0.07 bar. So H4 would be exactly equals to the HF at that pressure 0.07 bar. So that is 163. Okay. Now, to state point 5, now remember for any pump work, what we can do in order to find the enthalpy of H5 is to consider the work input of this. Okay, so the work input of 4 to 5 actually can be found by using this formula here, where this is the constant specific volume of saturated liquid. Because state point 4 here shows that is saturated liquid, and we assume that saturated liquid is incompressible. So therefore, this volume V4, or later on when you want to find state point 7, they are constants. So V4 or V5 or V7 and V6, they are all 0.001. Okay, so the pressure, so when you look at state point 4 and state point 5, they are actually between the pressure of 0.07 bar and the pressure of 3.5 bar. So you have 3.5 minus 0.07 multiplied by 10 to the power of 2. Because why? The pressure is in bar, so which is 10 to the power of 5. What we need is it to be in kilo, so that is why from bar 10 power 5 to kilo, so that is a difference in 2, so that is why we multiply by the 10 to the power of 2. So we got our work in of 0.343 kilojoules per kg, which is negligible small as compared to the work output, heat supply, or the heat rejected. So that is why at the beginning of the question, they ask us to neglect the effect of the feed pump. But then since this is the first example, we will go through by considering the work in. So work in, which is H5 minus H4, since we have got the work in, so from here, we can find out the H5. The H4, which we know it will be equals to 163. So from that, we would be able to find H5 at state point 5, that is the enthalpy at state point 5, which is the enthalpy of compressed liquid. This is in the compressed liquid region. So then we move forward with state point 6. Again, this is saturated liquid. So the enthalpy of this point here can be found by looking at the HF at the pressure of 3.5 bar. That is the bleed pressure, or the pressure at which the steam is extracted from the turbine for mixing in the open feed water heater. So H6, okay, from our table, which we have extracted from the property tables, you can just find the HF there and just write it down, okay, 584. Then state point 7 again. Now 6 to 7 is another isentropic compression of the pump, so we can use the same method here to find out the enthalpy of H7. So the work in, we have to calculate V6 and V4, as I have said, they are saturated liquid, and we assume that the saturated liquid is incompressible. So therefore, the specific volume for both are constant, the same value. So this is 0.6 is actually sitting at the blade pressure, and then 0.7 is actually sitting at the boiler pressure. So you just take the pressure difference between these 2 points here, which is 2 and 1. So you have 40 bar and 3.5. Here we do the same thing, times 10 power 2, so that we get the work input in terms of kilo. Then from that, we will be able to find out the H7. So then we have state point E, that is the saturated liquid at pressure 40 bar. So that is 1087. So now the next thing is what we need to do is to find the amount of steam that is being extracted for the purpose of the mixing process in the open feed water heater. So when you refer to this schematic diagram, we got to know that X kg is extracted, X kg of steam, and then it is at state point 2. So we can just simply write it as H2. And then when you refer to the open feed water heater, both of this is the same. So this would be the first inlet, and this would be the second inlet. So the second inlet is at state point 5, and which the amount of steam that is extracted here should be 1 minus X. Sorry, should be 1 minus X. Okay. Then state point 6, which is the outlet, this should be 1 kg because you have X plus 1 minus X. So you will have 1 kg. You get back 1 kg of steam, which is at the beginning of the process. You have 1 kg. So here you have 1 kg again. So 1 kg with state point 6. So you have inlet, inlet, and outlet. So you can consider now the energy balance and also the principle of conservation of mass. Okay, the mass balance. Okay, apply both, and you can write down, okay, an equation of X kg H2 plus bracket 1 minus X kg H5 equals to 1 kg H6. Then based on that, when you manipulate, you will be able to find out the X because we have already known all the enthalpies. So from this, we know that the X, the amount of steam extracted, is 0.19 kg per 1 kg of the whole, okay, system, okay, of the whole entire process. So per 1 kg. So initially, because we have already assumed 1 kg. So that is the final part. Then after that, we can find out what's the heat supply, the total heat supply, the total work output, and heat rejected, and so on. Because the first thing we need to do is to find out all the enthalpies from 1 to 7 is enough actually. So where is our heat supply? The first thing is between these 2 points. When you look at the boiler, okay, so actually you receive heat from here. So, and the boiler here is based on 1 kg. Okay, so this line here is based on 1 kg. So you can just take the difference between H1 and 7. So in order to find out the heat supply, heat rejected will be based on the condenser. The mass that you consider should be 1 minus X. So that is why when you multiply by the mass, it's not mass flow, okay? It's mass in kg. So that is why the answer should be in kilojoules. This answer also should be in kilojoules. So that when you look at this, the enthalpy difference and the amount of steam that we consider here, in this line here, what we have is actually 1 minus X only. So that is your mass should be 1 minus X here. So you get the heat amount of heat rejected is 1393.848 kilojoules without the per kilogram, because you have multiplied it by mass. So even though here it is 1, okay, I show 1 kg here so that, okay, you know how we got this value here with the unit of kilojoules only. So the thermal efficiency, you can apply this formula here to find out the cycle or the thermal efficiency or the cycle efficiency. Okay, or you can simply just put net work out over heat supply. So your net work out should be heat supply minus heat rejected, or work out minus work in, or simply by taking work out only if you neglect work in. That means neglecting all feed pump work. Okay, so that would be the cycle efficiency. And for the specific steam consumption, the same thing, 3600 divided by net work out. So you can take heat supply minus heat rejected, or only work out minus work in, and if you have neglected the work in. Okay, so you will be able to get the specific steam consumption of 4.39 kilogram of steam produced in the boiler in order to generate 1 kilowatt of power in 1 hour. That is specific steam consumption. Okay, thank you very much. That is the end of the slide, or the end of this problem. So there will be further problems in the later videos. Okay, please view. And thanks for listening or viewing my videos. Okay, so thank you, and remember, stay safe. Thanks a lot. Bye bye.